Welcome to today's Explainer. We're jumping right in because we have an absolute masterclass lined up for you. Now, if you've ever looked at a massive, incredibly dense list of chemical equations and instantly felt your eyes glaze over, well, you're definitely not alone. It happens to the best of us. But today, we're going to break down a seemingly endless list of chemical pairings into simple, beautifully predictable patterns. That's right, we are going to decode the chemical matrix.
So check out this number, 79. I know, it's a massive number, right? And it represents the sheer volume of individual, uniquely balanced chemical reactions we are literally going to decode from our source text today. Now, I get it, that might sound super intimidating at first glance, but I promise you, by the end of our time together, you're going to see exactly how manageable and logically structured this whole thing really is. Here is our roadmap for the breakdown. Section 1, the inorganic chemistry matrix. Section 2, Pillar 1, metals and acids. Section 3, Pillar 2, carbonate reactions. Section 4, Pillar 3, acid-base neutralization. And to wrap it up, Section 5, the final chemical equation.
Let's start right at the top. Section 1, the inorganic chemistry matrix, finding the patterns.
Moving right along to Section 2, Pillar 1, metals and acids.
Okay, so instead of trying to memorize 79 completely random equations, which frankly is basically a nightmare, we need to realize something crucial. Chemistry is beautifully governed by foundational rules. Honestly, think of these rules like cheat codes to the universe. Once you know the code, the whole matrix just reveals itself. Our source text pairs group 1 metals, your potassium, your sodium, or aluminum, with common acids. And when they mix, it's not random. Actually, scratch that. It's the exact opposite of random. It's a perfectly choreographed chemical dance dictated entirely by the elements involved. So here is our very first cheat code. Universal Rule 1, a metal plus an acid yields a salt plus hydrogen gas. I really want you to burn this exact equation into your memory, okay? Because this is the absolute vital key to decoding our first 30 equations. Every single combination of these metals and acids from our source will always produce a salt and hydrogen gas. No exceptions.
And this brilliantly illustrates the math of balancing. Let's look at the top line. We've got potassium plus hydrochloric acid. If we just smash them together, we get potassium chloride and H2. But wait a second. We started with 1 hydrogen atom on the left and ended with 2 on the right. We literally just broke the fundamental laws of physics. We have to count our atoms so that both sides of the equation are equal. So, by doubling the potassium and the hydrochloric acid, we perfectly attack for that H2 gas on the product side. Now everything is beautifully balanced. Make sense?
Let's actually see this in action. Notice how our group 1 metals, potassium and sodium, react perfectly uniformly across all 6 of our source acids. It's almost rhythmic. 2K plus 2HCl goes to 2KCl and H2. 2K plus 2HNO3 gives us 2KNO3 and H2. Now look down at the sodium block. 2Na plus H2SO4 goes to Na2SO4 and H2. Even with the bulky acetic acid, 2Na plus 2CH3COO yields 2CH3COONA and H2. It's a rhythm. Metal, acid, salt, hydrogen gas. Every single time. Scan down to the heavier phosphoric acid, even there. 6 potassium atoms easily balance out to give us our salt and 3 whole molecules of hydrogen gas. The rhythm never fails us. Now, what's really fascinating is what happens when we move over to calcium and magnesium. Because these specific metals possess a +2 valency, meaning, they have 2 electrons to give away, they require a slightly different mathematical ratio to balance out. You can clearly see calcium only needs 1 atom of itself to react with 2 molecules of hydrochloric acid to give us CaCl2 and H2. But look closely, the overarching rule remains absolutely identical: a salt and hydrogen gas. Notice how this specific valency perfectly dictates the math all the way down the list, even resulting in larger, more complex structures like calcium phosphate when paired with phosphoric acid. Finally, for Pillar 1, aluminum steps up to the plate, and with its +3 charge, it really escalates those coefficients. Just look at that first one. 2Al plus 6HCl yields 2AlCl3 and 3H2. The numbers are definitely getting bigger to make the math work, but it undeniably yields a salt and hydrogen gas every single time. Boom. That is 30 complex equations from our source text decoded, all just by knowing one simple rule. So seeing that incredibly consistent pattern really begs the question, what happens when we introduce carbonates to the mix? Well, this is where things get a little bubbly. Let's shift our focus to the second major group of reactants from our source text. Moving right into Section 3, Pillar 2, carbonate reactions. Let's see how this builds upon our foundation, replacing those raw elemental metals with much more complex carbonate molecules. Get ready? Here is cheat code number 2. Universal Rule 2. A carbonate or bicarbonate plus an acid yields a salt plus water plus carbon dioxide. The really crucial takeaway here is that by introducing oxygen and carbon into the reactant mix on the left side, we absolutely guarantee the exciting release of water and carbon dioxide gas right alongside our salt on the right side.
Just look at the pure, satisfying symmetry here as we matrix our 5 base carbonates across our designated acids. Potassium carbonate plus 2 HCl gives us 2 KCl, water, and CO2. And we see the exact same elegant pattern for sodium carbonate, calcium carbonate, and magnesium carbonate. Oh, and a quick side note on that last group, we've used the chemically corrected aluminum carbonate notation here, Al2CO33. When it reacts with 6 HCl, we get 2 AlCl3, 3 waters, and 3 CO2 molecules. The math scales up, but the rule never falters.
And the pattern just continues beautifully. Let's quickly cycle through the bicarbonates. Potassium bicarbonate, KHCO3 plus HCl, goes to KCl, H2O, and CO2. Look down at calcium bicarbonate with nitric acid. CaHCO32 plus 2HNO3 gives CaNO32, 2H2O, and 2 CO2. What you should truly take away from this is that despite the extra hydrogen hiding out in that bicarbonate reactant, our universal rule producing salt, water, and CO2 never, ever breaks. Honestly, feel free to pause and check the math on those super bulky aluminum reactions down at the bottom. The balance is totally flawless.
All right, Section 4, Pillar 3, Acid-Base Neutralization.
This brings us to the foundational bedrock of inorganic chemistry. When the remaining acidic and basic compounds from our list collide, something pretty incredible happens. They completely cancel each other's extreme properties out. Basically, an acid and a base walk into a flask, and they neutralize each other. And here is Universal Rule 3. Acid plus base yields a salt plus water. This neutralization process is arguably the absolute simplest rule to remember. The molecules are essentially just trading partners. The hydrogen from the acid and the hydroxide from the base link up to leave you with perfectly harmless water, and whatever is left over forms a salt. It's like a chemical puzzle snapping into place. Take a look at this. Unbalanced, we have sodium hydroxide plus sulfuric acid, giving us sodium sulfate and water. But wait, sulfuric acid has 2 hydrogens. Balancing neutralization is entirely about tracking those hydrogen and hydroxide ions to ensure every single drop of water is perfectly accounted for. So, to make the math work, we need 2 NaOH molecules to properly balance the 2 hydrogens in H2SO4, giving us exactly 2 molecules of H2O. Let's pace through these first 9 neutralization equations efficiently. Look at how cleanly hydrochloric acid strips the hydroxide away from sodium hydroxide to make NaCl and water. HNO3 plus KOH seamlessly becomes KNO3 and water. As we move down to sulfuric acid, H2SO4, we simply double up our bases to account for those 2 hydrogens, perfectly yielding 2 waters whether we are using NaOH, KOH, or even pairing it with calcium hydroxide, which natively has 2 hydroxides to give. It's so cool how that works. And now we wrap up our massive list with our final 10 equations. Even when we introduce trickier, bulkier molecules from our source text, like phosphoric acid, H3PO4, mixing with aluminum hydroxide, or acetic acid mixing with calcium hydroxide, just look at the results. H2C2O4 plus CaOH2 simply becomes CaC2O4 and 2 waters. The water and salt rule holds perfectly true across the board, every single time. And that brings us to Section 5, the final chemical equation. Huge congratulations, by the way. We have successfully decoded and completely balanced all 79 specific equations derived from some incredibly dense source material. Let's quickly review exactly what we accomplished today. Rule 1, metals plus acids give us salt and hydrogen gas. Rule 2, carbonates plus acids give us salt, carbon dioxide, and water. Rule 3, acids plus bases give us salt and water. Understanding these 3 simple universal rules completely eliminates the need for any rote memorization in inorganic chemistry. Honestly, it's all just pattern recognition. Which brings us to our final thought for the day. What other hidden patterns remain to be decoded in the molecular world around us? I really want to challenge you to take this pattern matching mindset into all of your future scientific learning.
Whenever things look impossibly complex, remember today's explainer. There's almost always a universal rule just waiting to be found. Thanks for joining me, and keep exploring.